Okay, this is going to be an overview and consideration of survival analysis. Just to point out, I'll be trying to suggest non-medical uses for survival analysis, just to keep things less than morbid. Okay, so survival analysis. Survival analysis is the study of time until the occurrence of a particular event. That event can be the passing of a patient or the failing of a mechanical product. Key survival analysis methods include the survival function, the Kaplan-Meier estimator, the hazard function, and Cox's proportional model. Of course, we can use functions such as SPSS, it's an area that has well-known practical applications, typically in the field of medicine and disease. Survival analysis is a range of statistical tools that we use for analyzing the occurrence of events with respect to time. These events of interest can be a binary variable, such as death, injury, machine failure, or of course we can have a continuous variable which has been coded into a binary variable, which simply means we'll include some parameters for consideration. So what are the uses of survival analysis? Well, the uses can be comparing different medical treatments, or comparing machine systems, for example. Now, one of the benefits of survival analysis, which is an important consideration, is missing data. Often we're presented with data sets that aren't fully complete. So we refer to this as censoring. So omitting certain aspects of data to make it better for application of the statistical analysis methods. We have two types of censoring. We have left censoring, where the subject's survival time is less than the time we consider, outside of the time frame we wish to consider. And we have right censoring, in which case the subject's survival time is more than the time which we want to consider. And of course, when people drop out of trials, so we also consider truncation. Now, similar to censoring, truncation is where we truncate the left and right to record an appropriate amount of data. And of course, censoring and truncation, well, they provide survival analysis with an upper hand over other methods. For example, regression. Because being able to manually manipulate or stimulate what you want from your data set means you get much more accurate and more telling results. So the first method that we're going to consider is the survival function, which is sort of the main function in survival analysis, funnily enough. So we consider PDF, probability distribution function, where T models the time remaining until an event occurs. The survival function is actually the complement of the cumulative distribution function, which is the integral of the PDF. And the survival function gives the probability of survival that the event has not occurred. I'll write that here. Event not occurred. Now for this we must write the survival function S of t is equal to the probability that t is larger than t, which is actually equal to 1 minus f of t, because f of t is the time that it fails, so we have 1 minus that, the probability, and that gives us probability of survival at time t. Now, unfortunately, survival function is monotonically decreasing, which means at every step of time difference we have, it can't actually increase on the point where it was, so it's constantly decreasing. The second tool that we're going to have a quick look at is the Kaplan-Meier estimator, a very useful method. So this is often used in medical fields. It's recognized as a successful estimator for the survival function. Now, the plot for the Kaplan-Meier estimator is depicted as a number of steps. Now, S hat t, well, this represents the proportion of objects or patients or whatever you wish to call it that have not experienced failure or the event by time t. And we write it as follows: St equals nt minus et divided by nt. So here nt is the number of objects at risk of failure. See if I can move this page up slightly. The number of objects at risk. And E is the number of failures at time t. Now, the plot for the Kaplan-Meier estimator should look something like this. Something similar to this, where the survival rate is here, and the number at risk is here. Okay, now we're going to have a quick look at the hazard function, which is one of the most important parts of survival analysis. The hazard function. It's actually a very useful tool for regression models. Okay, so it's denoted, or we display it as h of x. Now, it's a rate that denotes whether a subject will experience failure in a given time interval. It's defined as follows. So I have h of t equals f of t divided by s of t. Now here we have f as the PDF of relative survival time. And S represents the aforementioned survival function. Now, it should be noted that the hazard function, it's not a density or a probability. However, it's very useful when we're considering very small time periods. So if you have t to delta t, we can use it here. And the last statistical model is Cox's proportional hazards model. Okay, so this model actually takes into consideration the underlying factors at the time of failure. So, naturally, there are many covariates to consider. And Cox's proportional hazards model, we can express it as follows. So we can have h I of t is equal to the exponential to the power of alpha plus beta 1, xi1, and so on, depending on how many covariates we have. Now actually there is a manipulation method we can do with logarithmics to get it into a form whereby we don't have t as a consideration, but I'm not going to cover that here. It can be found quite easily online. So what does Cox's proportional hazards model offer? Well, it's beneficial. Because it's capable, as I mentioned, via manipulation, of actually removing time from hazard ratios. So, apart from medicine, where do we actually use survival analysis? So I'm going to give you two quick examples. We're going to call those practical examples. Number one is the famous, apparently, the famous prisoner example, which is quite fascinating. So, it was conducted by Rossi in 1980, and it was a study on 432 male prisoners. So it followed them, well, statistically followed them for 1 year after their release from prison. Now, the event failure, so the failure of event that we normally consider to be death in survival analysis, was actually the prisoner being rearrested. Now, the study was investigating whether giving the prisoners financial aid upon release actually had any effect. On them not being rearrested. So a very interesting study there. It doesn't always have to be medical, as is the next one, which is it's often used for claims data in non-life insurance. So obviously survival analysis features very heavily in the fields of actuarial science, particularly in the insurance industry. Now, it does make quite a lot of sense. For example, Kilding used a Cox model, and he used that to investigate occurrences of claims. These were obviously relative to the covariates of personality or to covariates of classification. Of the people in the study. So that gives you some methods to go forwards when proceeding with setting insurance. Now, we can actually apply well, I typically would use statistical software such as SPSS. So another example could be job duration. Now in the data set, we could have events. Quit, fired, and censored. In which case we choose one of these to be our event variable, another one choose to be our non-event variable, and censored would occur for every type of method of leaving your job or staying in your job that wasn't either 1 or 2 here. Then we assign these in a binary fashion on SPSS. So we have them entered as 1, 2 or 0 in the data set. Now in the output, having chosen an appropriate significance level, such as alpha equal to 0.05, one can actually conclude which factors affected the loss of job. And of course you can use Cox's hazards model. As I mentioned earlier, Cox's model of the hazard function to create a simple regression model. Now the joy of SPSS is that it does all the hard work for you, and also we can get some plots. So for example, we can have a hazard plot, time down here, and we can have a survival plot with time down here. Now if we're plotting the same graph here, it's quite difficult to do. That was meant to be flat there. And we notice that the hazard is going to have the same increase at the same time as survival here. So they're plotting the same thing, representing it in 2 different ways depending on which way you wish to present your data. So how do I conclude? Well, you have to say survival analysis, well, it's hugely useful, and naturally it's particularly useful in the medical field, though I have demonstrated many other areas and methods in which we can apply survival analysis without it being necessarily medically based. Why is it good? Well, it offers censoring, truncation, of course some regression methods, and a variety of visual argument form via the varied plots. Thank you for watching.